Hi everybody. Good evening. So I see only
Good,
five.
sir.
Evening. See only five of you. Maybe we'll wait for 2 more minutes. We'll start by 5:05 so that let everybody join. Okay. I think we'll start. If someone wants to join, let them join. Screen. So today is 10th. 07. Okay. Maybe before we start the class, we were speaking about one important thing last time, right? Supposed to be here. Is it this one? Or is it the fourth one? The four hearts. Right. So, which I just want to concentrate on the last part, which we spoke about. Right. So we were talking about titration. Right? This is what we started with, right? Okay. So titration is basically a process, right, by which I'll be able to find the unknown concentration. Say I have a solution. I know it is say NaOH or say it is HCl solution with me. I know what is there in the test tube, but I don't know how much is there. Right? I don't know the concentration. I don't know the molarity. Right. So titration is a process by which I'll be able to find this unknown molarity of the solution. Right. Fine. So in titration, there are going to be two components. One is what is called as titrate. The other one is what is called as titrant. Titrate is the one which is unknown. Right? We don't know the molarity. Okay. And volume will be able to measure. I think you hope you all know how will we measure the volume of the unknown solution. It is going to come from anybody knows it is going to come, volume is going to come from what? Volume of titrate will come from what? Anybody remembers? I told you that we'll measure this volume. How will we measure
From the
this volume?
standard flask, sir.
No. In standard flask, will I have the titrate or will I have titrant?
That will be titrant, sir.
Correct. Because we prepare the solution, titrant solution, we know the concentration, we know the volume, we know the molarity because we are preparing it. Right. Fine. Okay. Molarity we have to do from calculation, but this volume of the titrate, that is also called as analyte, which for which the molarity is not known, volume can be calculated. How do we calculate? I mean, volume you want to calculate, it is measured. From where it is measured?
Pipette, sir.
No. Again, pipette is again used for titrant, right? From the standard flask, you have to transfer it to the titration funnel, right? For that you use pipette. Now what else is remaining then? You told pipette, you told standard flask. What else is remaining?
Sir, Dessler or something, sir, starting with B.
Burette.
Sorry? Burette. That's what is the answer. Right. Anyways, so we will be measuring. Anyways, we'll look into it. Okay. So for titrant, that is, we are going to prepare the solution. We saw even how to prepare. Right. Anyways, so how we'll see first, the titrant first will be in the form of standard solution. Okay. Fine. So there will be something called as a standard flask. This is the standard flask which you see here. Right. And I told you that there'll be a marking. Okay, and depending on what kind of flask we have, this can be 100 ml, 200 ml, 1 liter, 2 liters, it can be anything depending on the marking. Okay, right. Now, so we'll be preparing it first. Say I want to prepare, so this is what is given to us. Say, assume that this is a 100 ml flask. Okay, now I want to prepare 2M solution. That is molarity, I want to prepare H2SO4, which is having a molarity of 2. And obviously, since it is a 100 ml standard flask, I'll be preparing 100 ml of 2M H2SO4. Okay, right, fine. Now, we have to calculate, we know that we have to prepare this H2SO4 solution of 2M, right? Hope you all remember how we did it. Say from the definition of molarity, right? From the definition of molarity, that is the molarity is 2. I know the definition says molarity is nothing but the number of moles of solute present in 1 liter solution, right? If I have 1 liter solution, whatever be the molarity, that is the number of moles of solute, right? Now, from this, what I can say, from this 2M H2SO4, I can say that 2 moles of H2SO4 will be present in total 1 liter of the solution. Right now, this standard flask, if this standard flask was 1 liter solution, I mean, the standard flask capacity is 1 liter. It's not 100 ml. Say if it is 1 liter, now directly I can take 2 moles of H2SO4, prepare the 1 liter solution. That's it. 2M solution is done. Right. But what we have, guys, it's only 100 ml. Okay, we have only 100 ml. Right. So for that, we have to calculate. So that what does that mean? For 2 moles of H2SO4, it is 1 liter. So for 100 ml, right, that is, you can see here, 1000 ml, 2 moles. For 100 ml, how much? It will be 0.2 moles, right? So for 0.2 moles, you know what will be the weight of it. You have to multiply it, the molecular mass, you'll be getting the exact mass of H2SO4 required for preparing this one, 100 ml of 2M H2SO4. Done. One part is okay. Right? We have prepared the standard solution using standard flask. Okay, right. Now I have to do the titration. Right? Titration in the sense the actual process. This is just the first part. This is not titration, right? So we have just prepared the standard solution. Now I don't need the entire 100 ml solution. Right? Making 100 ml solution, again, say going for 200 ml or something else, again, will be too much volume. Right. So we generally go for only 10 ml, 20 ml or 30 ml depending on the requirement. Right. So out of this 100 ml, I require, say, for example, only 10 ml. Right. I require, see, it's written here, 10 ml of 2M H2SO4 only required for the titration. See, this is not something, this you will decide by yourself how much you need. This can be anything depending on the requirement. So in our example, we took 10 ml. Out of this 100 ml, I require only 10. Right. So what we do for that, and that's where your pipette comes into the picture. Right. So pipette will be like this. Right. So there'll be opening at the top, there'll be opening at the bottom. Again, there'll be a marking. Right. So again, depending on the pipette, the volume will be different. Say it can be 5 ml, 20 ml, 30 ml, 10 ml. It can be anything depending on the pipette. Right. So what do you do now? You insert this pipette into the standard flask. Okay, you insert this pipette into the standard flask, then you put your mouth on the first opening and then you suck, right? You suck till the solution raises up to this level, the marking level, that is 10 ml. Okay, then once it raises, then you have to correctly close the thumb, right? So that the solution will not go out, right? So now you will hold it, you'll hold the thumb and you put it in the titration flask. Now this vessel, what you see here, you can see the pipette, right? You open the thumb and all the solution goes into the titration flask. So in this titration flask, what I have, 10 ml, it's a 2M solution. Obviously, we have prepared a 2M solution, but we have taken only 10 ml of this, right? So in this titration flask, all I have is 10 ml of 2M H2SO4. Okay, right. Now, the pipette part is over. Now what I have to do? Now I have to go for the actual titration. So before we go for the titration, we have to add some indicators, right? Because when I'm going to make the reaction happen, you don't know when the reaction will end, right? So we need to go for some indicator so that we will know the end point. There's something called as an end point where the reaction gets over, right? So at the end point, there is going to be some color change that indicates that the reaction is over. Okay, now in this case, we have used methyl orange. You can see here, methyl orange is there, and in acidic solution, it will have one color, and in basic solution, in neutral solution, it is going to have some other color, right? Fine. Now this setup is done. The titration flask will now contain 10 ml of 2M H2SO4, and also it contains methyl orange, little amount of methyl, 2 to 3 drops of methyl orange. Okay, fine. Now, what I want to find is the concentration of NaOH. Say I have a test tube containing NaOH. I don't know how much, what is the molarity of the NaOH. Okay, so that unknown solution I take. Okay, I put it this vessel which you see here is what is my burette. Okay, it's called burette, right? So this burette, inside this burette, I will fill the NaOH solution. Like you can see, it's unknown NaOH. It's filled here. Okay, now I'm going to fill this. Now there'll be markings on the side of the burette, right? So you have to fill it up to the brim. Until the last marking, there'll be a 0 marking there. Okay, until the last marking, you will be filling with the unknown solution. And in this case, it is the NaOH. Okay, right. And also there'll be a tap, right? You slowly open the tap, right? You slowly open the tap. So that drop by drop by drop, the NaOH will be going into this titration flask, right? So when it goes to the titration flask, I know what reaction will happen. H2SO4 and NaOH will undergo neutralization reaction. Correct. Now the reaction will keep on happening. You keep on opening this. So at a point of time, the color will change. That is, the methyl orange will go to red. The orange in color, it will go to red in color. The solution here will change to red in color, right? At that time, you close the tap. That's it. The reaction is over. Now, obviously, at some point, the NaOH would have come, say, until this point, right? Until whatever the dark marking you see here. You can even see my cursor, right? So until this point, assume that the NaOH has came out. Okay, and I will be able to measure this because all the markings are there. Say now 0, it came to 20 ml, assuming 20 ml. Okay, done. That's it. Now all we need is the reaction. Now reaction I know is H2SO4 reacts with NaOH to form the products, whatever products. Now all I require is the stoichiometry here. I require for 1 mole of H2SO4, I require 2 moles of NaOH. So the stoichiometric ratio. Okay, now I have taken what? I have taken, oh, this is 10 ml, right? I have taken 10 ml of 2M. Oh, I'm sorry. I'm really sorry. This is for H2SO4. Okay, so I have taken what? 10 ml of 2M H2SO4. Right? Now, what did I find here? I already know the volume. Volume I know here. Volume is basically 20 ml. I measured it from the burette. Right? Okay. Now, all I need is the molarity. That's what we already need to find out. Right? Now, for that, we need to do the normal stoichiometry. Right? What now? We already know how to do stoichiometry. Whatever data is given to you. Now, see the volume, molarity, volume, all the data are given to you. Now, you convert them into number of moles. Okay. So, when you convert them into number of moles, all I need, say, if you look at the formula, molarity into volume into molarity by volume into 1000. Sorry. Molarity is equal to number of moles by volume. No issues. Now, what will be number of moles then? Molarity into volume divided by 1000. That is the number of moles. I can easily calculate here. It would be 10 into 2 divided by 1000. So this and gets cancelled. So it will be basically 2 by 50. Whatever be the number. Okay, 2 by 50 will be basically 0.02. Okay, now I have 0.02 moles of H2SO4. Very simple. Okay, 0.02 moles of H2SO4 I have. Okay, now look, now you can do stoichiometry. For 1 mole, I require for 1 H2SO4, I require 2 NaOH, 2 moles of NaOH. Now what do I have? I have 0.02. How many moles of NaOH is required? We first calculate. Okay, now you can easily calculate for 1 this much, for 0.02 it should be double of that. So you'll find that it is going to be 0.04 moles. That's what we need, right? We require 0.04 moles of NaOH, right? Now, see, this is not the answer, guys. All we need is the molarity here. Okay, now you know the number of moles which is required. You already found out the volume from the burette calculation. Now you can easily get what will be the molarity. Molarity of this would be number of moles, that is 0.04 we calculated here, divided by the volume, which is 20 ml into 1000. So this can be going, say, 0 gets cancelled 50 times. So 50 into 0.04, 5 into 4, or say 0.4 into 5 is how much? 2 m. So the unknown concentration, what we have in this solution, in the burette, is basically a 2m solution. It's basically a 2m solution. Right? Guys, any questions you have, anything you want to ask me, sir, this I didn't understand, like any calculation part or the experiment part, any questions anybody has? Any questions? Okay. I suppose everything is okay for us. Right now, in the previous case, we calculated the unknown molarity of NaOH. Right, there can be other case where I want to find the unknown concentration of H2SO4 or some other acid. Okay, so in this case, what we can take is that the titrate, right? Titrate is going to be that is the analyte, right? This is the unknown concentration. Say this is some HCl solution. I don't know, right? And the titrant, I'd say it is NaOH, right? I know NaOH both molarity and volume. I know it both. Molarity is one, volume is also known. Okay, fine. Now there will be some changes here. Now tell me which, like if this is the case, if titrate is HCl solution and if titrant is NaOH, which will go into the titration flask and which will go into the burette? Tell me. If I have these two, titrate and titrant, which will go into the titration flask and which will go into the burette?
So HCl will go into burette and NaOH will go into standard flask.
Think about it and tell me properly. NaOH concentration, I don't know. That's the titrant, right? Oh, actually, I'm doing it ulta. Am I? Yeah, actually, I'm sorry. What you said was correct. Okay, my bad. What you said was absolutely right. Right, so actually I want to change this, right? This is actually, right. So anyways, what I'm trying to say is whatever is unknown, right? Whatever is the unknown here, right? Whatever is unknown, that only will go into the burette. Remember this, because from this we will calculate the unknown volume, and from the unknown volume, we then go for stoichiometry. Okay, and now, since I'm using NaOH, that is known solution, so in the standard flask or in the titration flask, I have to add the indicator properly. Now, in this case, the indicator would have been phenolphthalein, right? Because in basic solution, it is pink in color, and in neutral or acidic solution, it is colorless, right? So after the end point, you will see that the color changes from pink to colorless. That's what will happen, right? Okay, I think this is where we stopped last class. Right, and this is the example, same example which we took for the same thing. Phenolphthalein is there. Now H2SO4 will come. Now we found out to be 10 ml. Again, you can do the stoichiometry, however we do it. Okay, right? Fine. I think now it's time for us to do some problems on this. I think there is some chat. Is there? Sorry, I forgot all. Forgot to tell that. Okay, no problem. No problem. Tell Hamsini that's perfectly all right. Okay. Right. Fine. Let us take some problems. Guys, okay. And one more thing is, whatever we did till now, right? Whatever we did till now is what is called as acid-base titration. Okay, it's what is called as acid-base titration. Okay, right? And like I have other titration also. We'll have one more titration that we'll see later. Maybe today we'll complete it. Not a big deal. Right, so from the name we can understand we're talking about acids and bases. We'll be calculating, or we'll be calculating the unknown concentration of a base or an acid, depending on what is the requirement. Right? Okay. We will take some problems. Okay. Right. Take down 0.265 grams of, and please understand that in the question they will not give you burette, pipette. All these are important for your theory part. Okay, how you do the titration, right? But now you will see that only question in the form of stoichiometry. Like that's all we'll be doing, nothing else. Okay, right. So the problem doing part is much more easier than doing the actual titration part. Right. Fine. Take it. 0.265 grams of 0.265 grams of Na2CO3 required 0.265 grams of Na2CO3 required 28.5 ml 28.5 ml of HCl 28.5 ml of HCl for titration. For titration. Okay. Right. Now the question is, find the molarity of the HCl solution. Find the molarity of the HCl solution. Okay, I'll repeat the question, people. 0.265 grams of Na2CO3 required 28.5 ml of HCl solution for titration. The question is, find the molarity of the HCl solution. Okay. You can do the problem. It's pure stoichiometry. You just have to do like whatever be the data, convert them into number of moles, and again convert the number and do the stoichiometry and convert the number of moles back to whatever data you want it to be. Okay, that is how you do it. Convert into moles, stoichiometry, again convert back the moles into whatever you want. Very simple problem. It should be a very simple problem. So here the base is Na2CO3 and the acid is HCl. And guys, you have to know the reaction also. What will happen if I have Na2CO3 and HCl? Can somebody tell me the reaction? What will happen? The reaction part. Na2CO3 plus HCl gives what? Nobody knows. And this is supposed to be taught to you in your 10th class, acid, bases, and salts. The reaction part. What comes? If I put Na2CO3 plus HCl, what will happen?
So we'll
What
get
are the products?
H2 plus H2O plus NaCl.
Can you repeat again, Kanna? Sorry, I didn't hear.
So it will be NaCl plus H2O plus CO2.
Right, it will be, remember, whenever metal carbonate or metal bicarbonate is a base, obviously metal carbonates and metal bicarbonates are bases, but weak bases. Okay, anyways, so when these metal carbonates and bicarbonates react with HCl or means any acid, you will form the salt, water, and carbon dioxide will be released. Okay, now don't forget to balance this. If you do not balance it, and I think is wrong. Okay, so if I balance it, this will become 2 NaCl and this will become 2 HCl. All right? Yeah, right. Now you can do the problem. And I wanted to know, in your syllabus, do you have equivalent mass, number of equivalents? Do you have the equivalent concept at all? Do you have that? Did they teach you in school anything regarding this equivalent mass, equivalent number of equivalents? Did you hear anything like that, guys? Did you hear these words? Yes, no? Did you hear? Nobody knows. Did you hear this words equivalence?
Sir, we have heard it, sir, but I exactly don't remember whether they taught us this in school.
Anybody else remembers, guys? Did they teach you in school about this? Obviously, it is there for JEE and NEET. I know that.
Yes, sir.
But for CBSE, I'm not sure. Maybe I'll only look into it. Guys, anybody remember? Somebody should remember. You have been listening to the classes. I think you should remember. Anybody from school? Like, did they teach you this equivalence concept?
I don't think so, sir.
You don't think so? Okay, fine. Anyways, I'll also look into it. If it's there, we'll see it. If not, we can chill. Fine, yeah, we can do this problem.
Sir, is it 0.18?
0.18. Maybe. I'm not sure the answer. What answer is? We'll calculate. Keep the answer. Maybe I'll give you one more minute for everybody to get some sense out of this. So by today, we'll be completing this chapter, first chapter. And tomorrow's class, we'll be starting the atomic structure. Okay, any other answers anybody has? So let us look at what data they have given us, right? So they've given us 0.265 grams of Na2CO3, right? And one more data is known. The data known is that they have in the titration from the burette, from what I understand, is that I have 28.5 ml of HCl used. All I need to know is the molarity of this HCl solution. Simple. Okay, right. Now they have given mass. So whatever do? We just convert everything in terms of number of moles. So we'll talk about this volume later, right? This is just required for us to calculate the molarity. Okay. Anyways, now I have 0.265 grams of Na2CO3. This is mass, or I put small m. And if I have to calculate the number of moles, it would be given mass by molecular mass. That is 0.265. I think how much is the molecular mass of Na2CO3?
106, sir.
116.
106.
106. Okay, fine. 106. Okay. Any proper number is there or not? This divided by this?
0.0025.
0.002. Okay, so that is the number of moles of Na2CO3 I have. Okay, now from the stoichiometric equation, I can easily say that I have for one Na2CO3, right? We require 2 HCls. Okay, now how much I have? I have 0.002 moles of, this is from the calculation.
So actually 0.0025.
0.0025. Okay, we'll keep it like that then. Right, 0.0025 moles of NO2CO3. How much will be there? You see, it's double. 1 requires 2. So this, the double of this is what will be required. So can I say X would be 0.05? No issues. Okay, X would be 0.05. That is the number of moles of HCl. Number of moles of HCl is basically going to be 0.05. Now, what we need molarity, right? We have the number of moles, we have the volume. That's it. We just have to calculate the molarity. So that molarity of HCl would be number of moles of HCl, that is 0.05 divided by 28.5 into, because it's an ml, I put 1,000. Okay. The calculation is going to be a little difficult. Any answers here? This is where you got 0.18, someone said.
Yes, sir.
Okay, fine. So approximately the answer would be 0.18 m. Okay, actually we can calculate. Where is my mobile? We'll see whether it's correct. It is 0.05 divided by 28.5. Yeah, it's 0.175 is what I'm getting. Okay, this would be actual. The exact answer is 0.175 m. That's the answer. Yeah, approximately. But if you give 0.18, they'll not give you marks in the school. Okay, 0.175 is the exact answer. You have to calculate it properly. Right?
Okay, sir.
Yeah. Any questions, guys? Everybody understood? I hope it's easy. We didn't do anything like it's not as complicated as the actual titration part. This is just stoichiometry in terms of molarity. That's the only thing we are doing here. Okay, right? Maybe we'll do one more problem so that you will get a grasp of this. Right. Okay, right now. An aqueous solution of 6.3 grams of an aqueous solution of 6.3 grams of oxalic acid dihydrate. Okay, if you are wondering what is this, sorry, oxalic acid dihydrate. Okay, so an aqueous solution of 6.3 grams of oxalic acid dihydrate is made up to 250 ml, 250 ml. Okay, right. Now, what is the volume of 0.1 m NaOH? What is the volume of 0.1 m NaOH required to completely neutralize 10 ml of this acid? To completely neutralize 10 ml of this acid, that is oxalic acid dihydrate. Okay, right. Now I'll repeat the question, guys. An aqueous solution of 6.3 grams of oxalic acid dihydrate is made up to 250 ml. Right. Now, what is the volume of 0.1 m NaOH required to completely neutralize 10 ml of this acid solution? Okay, now it's exactly like titration. You prepare a 250 ml standard solution, and from that you take only 10 ml. And for that 10 ml, how much is the NaOH required? They have even given you the molarity, right? All you have to find is the volume. What is the volume required? This is like a little different not exactly different. The procedure is exactly same, but in the last step, instead of finding the molarity, you will be finding the volume because molarity is given to you. Okay, and anybody
So
wants
what is
to
the
know
formula of
Exactly. I was about to ask that. Anybody knows what is oxalic acid formula? Oxalic, okay, from it's a natural source, right? They have a natural source for oxalic acid, which is natural source.
tomato?
Tomato, okay, apple to some extent, right? So all this contains oxalic acid. Okay. So if you're okay, what is the functional group you need to have? You have studied carbon and its compounds, right? If it's a carboxylic acid, what is the functional group? What is the formula of the functional group? Sorry. So, for example, for alcohol, it is OH. For the what to say aldehyde, CHO. Like that. For acid, it is what?
This is only oxide.
Sorry. Okay, what is acetic acid formula? Acetic acid formula.
CH3COOH.
That is also carboxylic acid. So what is the functional group there?
CO.
Correct. So for
COOH.
any carboxylic acid, COOH is the functional group. And obviously you are going to have some other carbon or whatever it is there. Right. So anyways, for oxalic acid, it's a simple formula. It's COOH. That's it. Okay. So COOH. Then if you're wondering how exactly this looks, so this is going to be C double bond OH and again C double bond O. OH. So you see, for each of the carbon, 4 bonds are inside. 1, 2, 3, 4. Then 1, 2, 3, 4. Okay, that is the formula. And since it is a dihydrate guy, this is not the entire formula. So it will be COOH dot 2H2O. That is the entire formula. Dihydrate is there. Okay, oxalic acid dihydrate is COOH dot 2H2O. That's the formula. Now I think we can do the problem. It is exactly similar to the previous problem, little different, but again the one main difference is you have to find the volume and not the molarity. Okay, and if you're wondering about how the reaction will be happening, is anyone wondering what will be the reaction? So if everybody knows what is the reaction, I can ask someone randomly that what will be the reaction here. Can I? Okay, for that also there is no answer. Then let me ask. With that confidence.
Sir.
Yeah, tell me.
No, sir, we don't know.
Okay, so Prajit doesn't know. Fine.
Yes, sir. I also don't know, sir.
Okay, good. So when I ask you, why you're not telling? Anyways, cool. So if you look at this, fine. See, normally, like forget about this acid. Okay, normal the acid which you know, like let me take acetic acid that you have been familiar with, right? So if I had acetic acid, CH3COOH reacting with NaOH, normal acid-base reaction will happen. Right now, guys, hope you understand what is going to happen. The H plus, now remember, H plus from this, OH minus from this, together will form H2O. No issues. Okay, so one of the product here is going to be H2O. No issues. Okay, now whatever is left out, you just put that, right? Whatever is left out, what is remaining? CH3COO minus is remaining, H plus is coming out. Same way here, Na plus is remaining, OH minus is coming out. So what is left out? CH3COO, Na. That's it. Okay, CH3COO, Na is what we'll have the salt. This is called sodium acetate. The salt name is sodium acetate. The CH3COO minus ion, right? CH3COO minus is basically acetate ion, right? Now, same analogy can be used here, right? Now, COOH. Now, obviously, your 2H2O is there. If you want to write, you write, or else you don't write. Not an issue. Okay, 2H2O. plus NaOH. Right? Now, guys, please understand. Now there can be two H plus coming out. Right? You can have one H plus coming from this, another H plus coming from this. Right? So obviously, okay, actually for the sake of this thing, okay, fine, we'll put the 2H2O. Right? So obviously what you understand is I require 2 OH minus, right? I have one H plus here, one OH minus here, one H2O. Done. But here I have 2 H plus, one H plus coming from here, one H plus coming from here. So obviously I require 2 NaOH. So I have to put a 2 here. Okay, or you just forget about this 2, you can directly go for the reaction. So COOH, COOH, 2H2O plus 2 NaOH gives COONA, COONA plus 2H2O. That's it. Okay, more if at all you want to write, you can write 4H2O. Why 4H2O? Because already there is 2H2O coming, right? And also you have H plus, OH minus forming 2H2O. So totally I can have, 4H2O. Okay, so this particular, any guesses? What will be the name of the salt? From looking at here, can you tell me what will be the name of the salt? This is acetic acid. So the salt formed was sodium acetate. Now I know this is oxalic acid. So can you tell me what will be the name of the salt?
Sodium oxide.
Almost correct.
Oxalate, sir.
Oxalate, right?
Sir, I
Yeah,
thought
so
it's
this
funny,
is
sir.
yeah, no issues, no issues. Right, so it is sodium oxalate. Okay, right, fine. I think now you can do the problem, right? You know the formula, you know the reaction. But remember, in your exams, Akash Ramesh will not be there, right? You are on your own. So this time I helped you. But exams, if you believe in God, the so-called God should only help you, right? And I don't believe in God. Anyways, go for this.
Sir?
Yeah.
So usually in a compound, the basic element comes first, right?
Yes, correct, exactly. But when you go for organic substances, we write it like this. When I go for inorganic, this thing say for example, sodium chloride, I write sodium first, then chlorine, right? But when we have this organic compounds, we write like this generally. Like there is no reason as such. There is no perfect reason. This is what we have been following for the past 200, 300 years, and we are just continuing with that. There's no other reason for this. Okay. So you can do this. Yes, all of you are taking notes.
Sir, is it 1 liter?
1 liter. Can I 1 liter, that is 1000 ml? No. Check a calculation whether it is 1000 ml or I don't know. It cannot be 1 liter, obviously, because we
No,
are
sir,
using
1000
only
ml.
10
Does.
we are using only 10 ml of this acid, right? All we have to know, obviously, it cannot be 1 liter. Like that is too much, right? Even though I'm not doing the calculation, I don't think so. It will be 1000.
Sir, how is it OH plus? It should be minus, right?
Oh, I'm sorry. This is OH minus, absolutely. And I told it is OH minus, but I wrote it as H plus. Yeah, this is OH minus, absolutely. Yeah, guys, I wanted to ask, are you guys taking notes? I don't know how many of you are taking notes. Is everybody taking notes?
Yes, sir.
Okay, one confident answer I'm getting. What about others? Are you guys taking?
Yes, sir. Sir, but then
Yes, sir.
sometimes we miss some part while going fast.
Okay. While going
I
fast,
miss.
you
I
missed
don't know
something.
about others. I miss.
You can ask me at that time. So you can ask me, sir, you can hold on to the page. I'll copy this. You can tell me whenever you want it to like that. Okay.
Thanks, sir.
Whenever
Okay.
whenever you feel like I'm going fast, you're not able to take down, you can always ask me. Right. And guys, like I think I will check someday, some random day, I will ask you to, open your cameras and show me the notebook, what you have written. So be very careful. Okay. Be very careful that you're taking notes. Right. Now, taking notes has its own, like, hey, see, it's not, you're not doing it for me. I don't want to be a typical teacher, treating you like a typical student. Like that I don't want. But, at the end of the day, you are my students and I am your teacher. So there are certain times I have to behave that way. Right. But it's for your own benefit. Okay, if you are not taking down notes, right, reading the entire book is a waste of time. Okay, it's really a waste of time. Okay, because you have to go through sentences and sentences and sentences, so boring. But if at all you're gonna write notes in whatever way you will understand when you go through it, it will be very short notes, right? You can see, right? Like however I write, like just like that also you just copy how whatever I write, that also you copy, that also is more than sufficient. You really don't have to go through a book again. If not, then go for the big process. Go through the book, try to understand, watch some videos. I don't know, right? I prefer taking notes, right? And if you think that, okay, sir thought, anyways, I'm going to remember this, you will not remember. Even if it is Einstein who's attending my class, right? Say today I teach something 1 week or even one, like say 10 days after that, I ask you what I taught today, even Einstein won't remember. Remember this. We are not all geniuses here. Okay, so if at all you're not taking down notes till now, make sure you take down notes, and it is for your own benefit. You will not maybe understand now, but then the exam is approaching, right? Instead of going, I know obviously none of you will study till the exam. Even I am like that. I'm doing my PhD, right? Like say I don't study till the exam starts, right? Say 1 week or 10 days before the exam, right? You do the same thing, correct? And all of us want to get good marks, right? And if you want a good marks and study lesser amount of time, right? Taking notes is the only solution to your problem. Anything? I want to say something? Anybody?
Sir, is it 250 ml?
250. Why are you? 1 second. Which question?
Sir?
No, it's not 250. 250. See, we remember we are taking out of the 250 ml only 10 ml we are taking. If you are looking at the question very properly. Okay, it's not 250 ml. Yeah, someone wants to say something?
So no, sir, this might be wrong, but I got 2000.
Oh, yo. No. Like, see, it should be in the range of like say 10 ml, 20 ml, like that. You get something. Yes, I can considering logic. Yes, that might be correct. Say 250 ml, more than 50 ml is itself is wrong. Like I can tell without the calculation. Okay, maybe I will do it. Right. We'll write the reaction again. Right. So it's COOH dot 2H2O and plus 2NaOH. Okay, this is all I require. Products. That's it. I don't need to worry about the products. This is all I require. 1:2 is the ratio. 1 here, 2
Sir,
here.
is it 10 ml?
Possible. Option is there. Okay, 10 ml option is there. Might be correct. We'll check. Okay, fine. So now what data is given to us? They have given initially 6.3 grams of this oxalic acid is there, and 6.3 grams, and it is diluted to 250 ml. Okay, this is diluted to 250 ml. Now itself will calculate the molarity, people. Okay, molarity you can easily calculate. So can someone tell me what will be the molecular mass of this? COH, CO2, H2O, what is the molecular mass?
126.
126. Okay. So now if I calculate the number of moles of oxalic acid, right, that would be 63 divided by 126. So it should be 1 by 2, 0.5, 0.5, 0.05 moles. Right. So basically I have 0.05 moles of what is that? What I'm saying, oxalic acid. Okay. Now we'll calculate the molarity of the oxalic acid. Right. So that would be 0.05. Right. And volume is 250 ml, guys. Now you have to do only with this volume. From this 250 ml, we take 10 ml. Remember that. Okay. When you calculate molarity, you calculate like this only. Okay. So 0.05 divided by 250 into 1000. So this will go 4 times. So it should be 0.2. Okay. So the what do you say? So the molarity of this is basically 0.2 m.
Oh, sir.
Yeah.
Sir, but why do we need to calculate molarities?
Why do we need to calculate molarity? It's because from this, okay, if I do the calculation, understand, just we'll just try to follow, right? We will understand why we are calculating molarity. Okay, fine. So now we have calculated the molarity, that is 0.2 m. So what do I actually have? I have 250 ml of 0.2 m oxalic acid. This is what I have, right? But from this, I am taking only 10 ml. Right? So what I have is basically 10 ml of, so what I'm actually, sorry for the background noise. So what I'm actually using for the titration, what I'm actually using is 10 ml of 0.2 m oxalic acid solution. This is exactly what we are using for our titration. Because 250 ml of solution is prepared, that is the standard solution. Out of it, only 10 ml is taken for the titration. So 10 ml of 0.2 m. 0.2 m we calculated from the mass, we know calculated the moles, and I know the volume, so I know the molarity. Okay, now this should be converted into number of moles again, right? If you do not calculate what is the molarity here, right? If you didn't calculate this, how will you know what is the number of moles? If you have calculated number of moles using the 6.3 grams, it is absolutely wrong. Okay, because 6.3 grams is there in 250 ml, right? So, but what I need is only 10 ml out of this. So obviously, it is better to convert this into molarity. That is, say we can say that 250 ml of 0.2 m oxalic acid is there. Out of it only 10 ml is taken. So what we need for a titration is this 0.10 ml of 0.2 m COOH. Now you understand why are we calculating molarity?
Sir?
Yeah.
Sir, instead of calculating molarity, we can say that for 250 ml, 6.3 grams is required. So for 10 ml, we can calculate.
Absolutely, you can do that. Why not? Okay, you can do that. Right, but this is, since we are talking about, that will be a shorter method. But since we are doing the titration part, that's why I had to bring in molarity here. Okay, but that would be a shorter method. Yes, for 250 ml, it is 6.3 grams. For 10 ml, how much? Yes, absolutely, it will work. No issues at all. Right? Okay, so now this we have. Right now, there is 10 ml of 0.2 MnOH. Sorry, see this oxalic acid. Right now, I can calculate the number of moles again. Right, because I need everything in terms of number of moles. Now they have given the concentration of oxalic, NaOH to be 0.1. Right, 0.1 m. I need to find the volume. Okay, guys, if you don't want to, convert into number of moles and whatever, right? You can always do like this, right? This in your school, they would have taught you like this only. M1 V1 equal to M2 V2 This sort of stuff they have taught to you, right? Did they teach you like this? M1 V1 equal to M2 V2 and all? Did they?
Yes, sir.
Okay, right. They would have taught you this, right? This is nothing. This is nothing but now M into V will become number of moles N1, and this would become number of moles 2. That's exactly what we're trying to do here. Molarity into volume is going to give me number of moles. That's what it is. Okay, but you cannot directly tell that M1 V1 equal to M2 V2, but you have to look at the stoichiometry, right? So this is M1 V1 N1, right? So you can see the stoichiometric ratio is 1:2. Right? For 1 mole of this, I require 2 moles of this. Okay. But again, if you don't want to get confused, we'll calculate the number of moles normally, then go for the number of moles here. Right? So I'm calculating number of moles of CO, that is oxalic acid. Right? Now that would be molarity into volume. That is 10 ml into 0.2. Right? So that would be 10 into 0.2 divided by 1000. Right? So that would be 0.0002, correct? Moles, right? 0.0002 moles, right? Okay. Now that's it. Now you can easily calculate for 1 mole of this, I require 2 moles of this. Now what I have here is 0.0002 moles, and here I should be having the double of that. So it is going to be 0.004, that is 0004 moles of NaOH. No issues, right? Now you can easily calculate the volume now because I know the molarity 0.1 m and I know the number of moles also. So molarity is equal to number of moles by volume. So now molarity is 0.1, number of moles is 0.0004, 1 more 04 divided by the volume which we don't know into 1000. Right? Let me rub this part. Into 1000, right? So volume will be how much? Volume would be 0.004.
Sir?
Yeah.
Sir, wouldn't it be 0.0024, sir, not 000?
I don't understand what you're telling. 0.
No, sir, it should be 2 zeros and 4, 0.004, not 0004.
Okay, so when I calculated the number of moles of oxalic acid, it is coming as 0.2 divided by 100. 0.2 I'll divide it by 100.
Yes, sir. So 2 zeros only.
Correct. Only 2 zeros. Yes, absolutely. Yeah. Okay, 2 zeros. Okay. So this 0 is also getting cancelled. Okay. Right. So it is going to be 0.004 divided by 0.1 into 1000. So this is basically going to be 4 divided by 0.1, or I can write 40 divided by 1. So basically that is going to, the answer is going to be 40 ml. That's the answer to this question. Nice. Hope you all understood what I'm doing here. Nothing like say first step, right? First step is calculating the molarity, or if at all you don't want, you can go by the method. I don't know who told, that student told, right? You can use that 250 ml or for this much. So if I have 10 ml, how much that you can do, right? And then you can do the, even stoichiometry normally, or you calculate the molarity now. You got that molarity as 250 ml because you know you can calculate the number of moles. You know the volume. You can easily calculate the molarity 0.2 m. Right. So out of this, only 10 ml is required. So what we have is basically 10 ml of 0.2 m oxalic acid. Done. Next, you go for normal stoichiometry. That's it. Normal stoichiometry. Now, instead of finding the molarity, you calculated the volume, and the volume you found to be 40. 40 ml is the answer to this question. Okay. I hope everybody is clear on what we are doing here. Simple questions. What is the time? Okay, we still have half an hour. Right. So yeah, that is about acid-based titration, guys. Right. Any questions anybody want to ask? Okay, fine. I hope everything is clear. Right.
Sir, do we have any notes of this chapter, like other than our running notes?
Other than
our own running notes, does
Okay,
Echelon itself provide any notes for chemistry.
They will provide you a book, correct? Did they provide you the book?
No, sir, they didn't do that.
Oh, a book has to be provided. Maybe you can ask them. I think they have to, but maybe they are waiting for you to come to the camp, come to the this thing. What to say? Come to the center and collect it. Maybe after the lockdown opens and all, they will give you the thing. Okay, but again, I would suggest, even though they give you a book, right, even though they give you a book, it is better that, like, you take running notes. Okay, and actually I can also, like, whatever notes which I'm writing, okay, now that also I can give you. Okay, this can be given in terms of a PDF, whatever, not only for this class, from the starting till this class. Okay, whatever I wrote here, if at all you're okay with it, that's all, that also I can give you. Are you okay, guys? Can I give you this?
Yes, sir. Can you please give it, sir?
Yeah, okay, but you understand, right? I have a very clumsy handwriting. It can be little shabby, but if at all you can manage with this, you can manage. I can send you, not a big deal at all.
Sir, if you have any
Yes.
doubt, we'll message you, sir. You can send it.
Yeah, no. Do you guys have a group for you in WhatsApp? Do you guys have
Sir,
WhatsApp group?
no, sir. The group in which you sent the link, sir, that is only the group.
Oh, that I am not there. In that group, I am not there. It is only, I think, for the communication purposes. Can we do one thing? Can we have a group? Say whatever be the number of students. I think we have 13 students here. Like totally, the total strength is 13. So if someone can take the responsibility of collecting the numbers and making a group. You also have my number. I can send the thing there. I can send the notes there. Or whatever the problems, whatever discussion we can have there. Or I will send the notes to excellent people, right? And I'll ask them to post them in the group which you have. That is also fine. Okay, right? Let me see what I can do. But you will get your notes somehow. Whatever the notes we have, right? I can send you that. Right? So that will take care. Now it will be along with the dates. You don't have to worry. Like, I'll put the dates accordingly, and then I'll send you. Okay, fine. Now the last part of the chapter, people, we are entering the last part of this chapter. Okay, that is redox titrations.
Sir, actually, I have a doubt, sir.
Yeah.
Sir, these titration parts, they have never taught us in a school. So, is this there in CBSE?
Really? They didn't teach you this?
No, sir.
Oh, wait.
They never taught us even the acid-base titration.
Really?
Yes, sir.
Sir,
they only taught us the M1V1 method, sir.
Oh, maybe they wouldn't have mentioned that, like this M1V1 is for the titration, but it's actually for titration. This and all, they must teach you. How will they not teach you? Let me check in the book, guys. Just give me a moment. I have to download your. Anybody has your book, guys, with you? CBSE textbook with you?
Yes, sir.
Yeah, just open it, no, and go to this chapter. Some basic concepts of chemistry. And check whether these titrations are there or not. It is there, because when I studied, it was there. So they didn't change the book till now. So it should be there. Is it there?
Sir, there's no separate subheading for titration, sir.
Correct. Yeah, there will not be separate titration. But did you see, are you seeing burette, pipette, acid base, redox, anything you're seeing like that?
No, sir.
Let's see, one second. I'll download, guys. 1 second. Chemistry. Chemistry part 1, right? Yeah. Chapter 1 is what is it chapter 1? Is it whatever we are talking about?
Yes, sir.
Oh God. This and all they're teaching. This and all, guys. Do you want me to teach all this? Gas, solid, liquid, gas, matter. What are they? All these stuff you need to know, or really, this and all I already studied in ninth class. That's why actually I didn't, you know, teach you. But if at all you want me to teach you again, not a big deal. Okay. Volume, uncertainty, scientific notation, everything you'll study in physics first chapter. That is the dimensional
Yes, sir.
analysis, right? I don't want to actually spend some time on this. Okay, law of conservation of mass, law of constant proportion, multiple. Gay-Lussac's law, why is it coming here? It will come in the next chapter. Don't worry, guys. This one all we'll look into gaseous state chapter. Don't worry. This is Avogadro's law. Gay-Lussac's law. We'll again see it. Don't worry that we didn't see it. We will see it. Don't worry. And this is actually where we started the chapter, atomic and molecular mass. Oh God. Percentage composition, empirical formula, all these things we saw. Limiting reagent, stoichiometry, balancing, mass percentage, mole fraction. Okay. Oh, that's it. You don't have titrations. Great. Why did I teach you? But do they have any questions like that at least?
I don't think so.
Yeah, they don't have. But you will be doing this in the lab, that I know for sure. Because lab, the one of the experiments you will be doing is titration. Actually, titration, 2-3 experiments you will do. One for modes of salt, all these things you will be doing. Okay, I think this is where
Sir?
Yeah.
Sir, but you told titration is for practical purposes. Maybe they'll
Correct,
teach
correct.
practical.
That's why they didn't teach you. But again, it's very important, people. Titration, why we are studying, like the whole point of doing stoichiometry is titration. That is what that is where you're going to use it. Okay, at least now that you know this, right? Actually, we can go for the next chapter because redox titration, again, it is a little more not complex, but for you to study, you have to understand what are redox reactions first, and then only we can actually move on to this. So we don't have to spend time on this. Okay, right? Cool. Maybe we'll close this part and we'll go back to our. So yeah, the redox titrations we'll not see. Okay, but if at all anybody is interested, right? Maybe we can have an extra class and look into this if anybody is interested. Okay, fine. Then we'll go to the next chapter. Guys, anything you want to ask, right? Actually, we saw so many things and we did. Okay, guys, maybe I'll give you the like whatever I missed in the like say the first part of the chapter that is talking about, you know, matter, solid, liquid, gas, all these things you want to learn now, or can you go to the next chapter?
Sir, we can go to next chapter, sir.
Okay, because that is anyways easy, and your school would have spent so much time on this, right?
So
Okay.
on which part, sir?
Sorry.
On which concept?
No, that you know, what is matter, or how is matter classified? Solid, liquid, gas. How are they different? What is volume?
Yeah,
all
okay.
that. Right. That part alone we didn't teach at the starting also. We directly went for atomic mass concept, and then we went for what is that, concentration terms, and then we went for stoichiometry. That alone is there. And lastly, we saw about this thing also. What is that? Our titrations also. Okay, fine, cool. So now we will, what is the time? 12. Okay, cool. Start. Okay, right. So as I told you, this is one of the very interesting chapters, right? And this is going to be you like if like no irrespective of what you are going to do in your future, right? Whether you're going to do engineering or whether you're going to do medical or what you're gonna like, unless until you're gonna like what to say, you're gonna become an accountant, and that is not possible since you have taken 11 science, right? If at all you're not going to switch your career like that, you will be using whatever I'm going to teach you in this chapter till you study, or even if at all you're going to continue in science, you will be using this for the end of your life. Okay. So in this chapter, what and all we'll see is we'll first talk about the history. Okay, like different atoms were made, right? We know what is atom, right? Well, atom is basically the integral part. Say it is the building block of matter. Every matter has atoms in it, right? So scientists try to give a structure to the atom. See what is inside the atom, right? See, even now, guys, even now, right, we will not be, even though the most powerful of all the microscopes, right, we will not be able to see what is we'll not be able to see the atom even with the help of a very strong microscope, right? So it all has to be purely theoretical and little amount of experiments, but not like exactly looking into what exactly it is, but say with the help of some okay, this reacts with that, okay, this happens when I give some electric field, this happens when I give some magnetic field. So based on those kind of experiments, scientists try to give some structure to atoms, how they look, what is inside, what are the constituents. Okay, so like say 75% of the chapter, right, 75% of the chapter will go into the history itself, right? And the last 25% we will be looking at what exactly we are using today. Okay, and that is what is called as quantum mechanical model. Okay, so that we'll see. And I told you, maybe if you can remember, when we had the orientation class, in the first class, what all chapters are there, what will you study in those chapters, I told you that we are going away from this KLMN rotation. We are not going to anyways use this. Okay, now we will be talking in terms of this S, P, D, F, all these stuff we'll be speaking about. Okay, we are not anymore in lower class, so this is gone too, right? K shell, L shell, M shell, all these are gone. Okay, but again, this SPDF will come only at the end of the chapter, like how we do it, what are these, how they even came into the picture, how exactly they will look, right? All these things will come in the last part of the chapter. And guys, if you are not going to concentrate, at least in the last part of the chapter, this SPDF part, when I teach you, and you're not going to concentrate, your 11th and 12th chemistry, that subject will say sorry to you. Like instead of you telling sorry, right, the subject will say sorry to you if you are not going to concentrate on this particular part. Okay, the other part is as well as important for your 11th, right, for your especially, okay, if at all I tell you, right, we'll start with Dalton's, right? Again, we all know what Dalton said, and then we will go for J.J. Thomson. And this is the most, I would say, this is the very interesting part, Thomson's part, the cathode ray experiment part. Okay, we'll see what and all he did, how we gave the plum pudding model, so on and so forth. And then we'll see the Rutherfords. Okay, now till Rutherford, there is one era of science. Okay, the one era of chemistry, I would say, right? After Rutherford, there was this guy, okay, who revolutionized science. Okay, and that guy's name is Planck, Max Planck, right? In Germany, we have an institute, Max Planck Institute. Okay, now what is so special about this guy is all of you know Newton, right? Newton in physics, right? So Newton is like a don in science field. Like nobody can talk against him. Nobody, even the church people will find very afraid when they want to oppose Newton. He's like a don, very strong guy. It's not strong in terms of body, but very strong in terms of influence in the scientific field. Okay, so this Max Planck was the first scientist to tell that Newton, you are wrong, and he proved it, right? We'll see how and all he did it. Okay, this Max Planck guy, right? He actually disproved Newton. Not only chumma saying that you're wrong, right? He actually proved him that no, your concept is wrong. Not entirely wrong, a particular pace. Like if at all you want me to tell you what exactly it is, we know you're studying about Newton's first law, second law, third law. All these are for motion, right? How a particle moves with respect to time, right? And distance, displacement, all these stuff. You know the equations are there, right? So when Max Planck tried to involve this equation for the movement of electrons, we know there are going to be electrons inside the atom, and the electrons are also moving. They are also in motion, right? So when the Newton's laws of motion, when the Newtonian equations were applied to electrons' movement, they were not coming out to be good. Okay, so he said that is where the science, the mechanics part, the mechanics is basically about the movement part. Mechanics, I'm sorry, not mechanism, mechanics was divided into two things. One is the classical mechanics, that is your Newton, right? That is for normal, say for human beings, for you can apply it for, planets, you can go for, moon, sun, all these things can be done with the help of classical Newton physics, right? But when you go to subatomic levels, right, that is where your quantum mechanics come, right? So the introduction to quantum mechanics was given by Max Planck. Okay, the introduction to quantum mechanics was given by Max Planck. Okay, so we'll see all this in detail, but not so much detail, but we'll see like how much ever you can understand. Like again, I'm telling you guys, not only for this chapter, any chapter, it's like I am like an encyclopedia, right? If you want to search, if you want to get answers, you have to ask. Okay, and I'm pretty okay with the amount of questions you're asking, but I would say it's less. Right, I'm getting questions only from very few people, like say repeated faces. That's what, like, I'm just telling this in the previous chapter experience. What happened in the previous chapter? The number of questions were pretty less, right? And I'm telling you, the more and more questions you ask, more and more things you're gonna get out of my mouth, right? Like, you can ask me, sir, even though I don't ask that out, you can tell you, like, you can tell me, right? Yeah, I can tell you, but I feel like, say, I will be telling you things which I think you will understand. Okay, now I can tell so many things, I know so many things, but if I tell you, will you understand is the question, right? So I will tell only things which I think that you will understand. If I think that you will not understand, I will not tell it. Okay, but if at all you have any curiosity, right, you are always welcome to ask any kind of questions. Anyways, so now after Rutherford, we'll study about this Max Planck. It's called quantum theory. Is it called quantum theory? Okay, anyways, it's called Planck's quantum theory. Yeah, it's called Planck's quantum theory. Okay, we'll study about this, and from this only again a revolution happened, and that's where your Niels Bohr came. Right, Bohr's atomic model. You studied in 10th class or 9th class, whatever class it is. Okay, Niels Bohr came. Again, Niels Bohr is based on this quantum theory, but it has its own problem. Okay, so at last we'll move to the thing which we are using now, and that is what is called as your quantum mechanical theory, and that is where this SPDF, all these things comes. Okay, so this is the flow chart of the entire chapter. Okay, and in the, like, say, these things are very easy. Okay, J.J. Thomson, Rutherford, till now it is very easy. Max Planck, like, we will not see much. We'll just give you the introduction. So, but this part, Niels Bohr's part and the quantum mechanical part is very, 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 very important. Okay, now Niels Bohr's part you already studied in your lower classes, but you wouldn't have done any calculations. There are a lot of formulas, there are a lot of numbers coming. Okay, so that we'll do, and obviously in the quantum mechanical model, this introduction of SPDF and all is very, very important. Okay, so this is the entire flow chart for your chapter. Okay, so maybe I will stop with this for today, even though we have 10 more minutes. We'll stop with this for today. Okay, so tomorrow's class, I'll be starting with Dalton Steel, you already know, J.J. Thomson's, we will directly go for your cathode ray experiment. What exactly he did, how from the cathode ray experiment, how he was able to give the plum pudding model. We know only about the plum pudding model. We don't know the experiment behind it, right? We will look at the experiment and we'll see how, actually, before this, right, before even we go for Max Planck, after Rutherford, we'll be seeing about, say, now J. Thomson discovered electrons, this guy discovered nucleus, and we will have how neutron was discovered, how protons were discovered, all these things we'll see. Okay, and then only we'll go to Max Planck. Okay, so this is the entire flow chart of this chapter. Beautiful chapter, very, very important chapter, a beautiful chapter. Important in the sense, not with respect to your marks, with respect to your knowledge, with respect to you to understand and appreciate the subject, right? This chapter is very, very important. Okay, right? So I think we'll stop with this for today, people, right? Is there any questions you want to ask me? Is there anything you want to know? Anything else? Okay, fine then. I think we'll stop right here. Okay, and you can actually go take rest. Tomorrow again, we'll see. Thank you so much, people. We'll meet again tomorrow.
Sir.
Yeah.
Sir, tomorrow I won't be able to coming, sir.
Sure. Then you can see what is that? You can see the recorded session. It will be recorded and given to you. You can look into it. And if at all you have any doubts, you can always personally message me after that, after watching it.
Okay, sir. Thank you, sir.
Right. Okay, guys. Thank you so much. We'll meet again tomorrow.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.